He will talk about behind, not invariants and Hilbert.
Okay, so thank you very much for inviting me to this conference and for the possibility to give a talk. So I will speak about Hilbert scheme of points on C2 and some variants of those and some interesting sheaves on Hilbert schemes and some interesting relation to node invariants and so-called refined node invariants which were recently defined by physicists and more classical node invariants such as Holmes-like polynomial. So the plan is that I will spend some time discussing classical facts about Hilbert scheme of points on the plane, and then nested Hilbert scheme of points on the plane which are not so known, and then I will construct some interesting sheaves on them and operators in K-theory, and then I will explain how this is all related to invariants of these some nodes. So, what is the Hilbert scheme of points on C2? So, there is a symmetric power, which is the easiest possible construction that you may think of. It's the moduli space of unordered n tuples of points on the plane, and it's known to be very, very singular if the number of points is 2. And there is a nice resolution of this thing, which is called the Hilbert scheme of points, and this is the moduli space of what I mentioned n ideals in the polynomial ring. So if you have such an ideal, it is supported on a finite number of points, and the total multiplicity will be m. So this defines me a Hilbert homomorphism from the Hilbert scheme of points to symmetric power of C2, and the classical theorem of property said that Hilbert scheme of points is smooth, and so this morphism is actually a resolution of the symmetric power of C2. So another important thing that we will need is the torus action. So there is an action of C star squared which acts by dilation of coordinates on C2. And you can lift it to the action of C star squared on the symmetric power where we just move every point by this dilation. And we can also lift it to the Hilbert scheme of points because we can scale the coordinates and we can scale the ideal. It will be a different ideal after the action, but the action is there. And one can check that there is a finite number of fixed points. They correspond to monomial ideals, and this is one example of a monomial ideal, which is generated by 4 monomials y cubed, xy squared, x cubed y, and x in power 4. And all such monomial ideals are in one-to-one correspondence with Young diagrams, as you can see. So the white area below the red line is actually a Young diagram with, in this case, how many? 1, 2, 3, 8 boxes. So this represents an ideal of codimension 8, and all fixed points in the Hilbert scheme of n points will be represented by Young diagrams with n boxes. So this is all quite known and classical. So a bit less known, but still quite classical object is the punctual Hilbert scheme. So the Hilbert scheme of points supported at the origin, where which can be considered as just scheme theoretic fiber of the Hilbert homomorphism over 0. So all points, all n points, should be supported at 0 with multiplicity n. And then the punctual Hilbert scheme is in general much worse than the full Hilbert scheme. So for example, if the number of points is bigger than or equal to 3, then it is singular. So one example is that Hilbert scheme of 2 points supported the origin at the projective line, so it is smooth. But Hilbert scheme of 3 points supported the origin is a cone or twisted cubic in P3. So this is already quite non-trivial and singular object. And for example, it's not a complete intersection, and it is quite subtle thing to deal with. So the vertex of the cone is actually the monomial ideal, and you can see that there are 3 fixed points of the torus section which correspond to these singular points, and 2 non-singular Young diagrams which are line and another one. So one positive thing about this punctual Hilbert scheme is that a theorem of part of it was proven by Bramson in 70s, I think, and by Haiman in 90s. that it is actually reduced. So if we define it as scheme-theoretic fiber, we need to check if it is reduced or not. But it is actually reduced, irreducible, and Cohen-Macaulay. So the last fact I think was proved by Haiman. And its dimension is equal to n minus 1, as we can see in this example. But again, the geometry is not so obvious, and somehow we will need a partial resolution of this Hilbert scheme supported torus. Okay, so we'll need some sheaves on this thing. So again, one classical sheaf that you can think of is the topological bundle over the Hilbert scheme of points on C2. So this is rank n vector bundle whose fiber over a point represented an ideal I is just the quotient of polynomial ring by I. So this is the ring of functions on this zero-dimensional scheme represented by this ideal. And we can also consider the symmetric parts of this thing, exterior parts of this thing, and there are all the most tautological bundles on the Hilbert scheme. And by some technical reason, I will need what is called Adams operations of T. So these are some formal classes in equivariant K-theory, which are defined by this equation. So if you never saw something like this, that it's hard to understand why this is interesting, but somehow symmetric powers correspond to some, especially exterior powers correspond to the symmetric functions and in Chern roots of this bundle, and these guys correspond to power sums of Chern. But again, it's not so important, and it's kind of technical, so you can think of just exterior powers of T. And then, of course, there are some operators in K-theory of Hilbert schemes which are just tensor multiplication by these classes. So again, by exterior powers, by symmetric powers, and by this French PK, which are more relevant for us. So okay, so all this was about Hilbert scheme, and all this is kind of classical. So another piece of classical information is that there is a correspondence between Hilbert scheme of n points and Hilbert scheme of n plus 1 points, consisting of pairs of ideals, I and j, where I is sub-ideal in j. So j has codimension n, I has codimension plus 1, and then if one is inside another, this is some correspondence in the product of these two. And then a remark which was, I don't know the story, but I guess the first proof was by Janchia, is, and also proved by Tikhomirov, Elensrud, and other people, that this correspondence is actually smooth. So we can use it for many different applications. And there is a natural line bundle on this Hilbert scheme of n plus 1, which is defined as the quotient of j by I. So the fiber of it is one-dimensional because the difference of codimension is 1. And we can actually define some interesting operators in K-theory of Hilbert scheme using this line bundle and this correspondence. So we can start from some sheaf E on the Hilbert scheme of n points. Then we can pull it back to the product, to the correspondence, twist it with some power of line bundle, and in principle this K can be chosen arbitrarily, and then push it down to Hilbert scheme of n plus 1. So this defines for me some operators which I will denote by P1, K. And the notation will be clear. So again, more classical object would be the same thing without twisting by line bundle. This is used all over the time in the Hilbert schemes, but if we choose different K, we get in principle different operators, and all of them are quite important. Okay, so now how this can be used. So recently new result is a theorem of Shipman and Vassara, and also independently by Fagan and Simbaluk, who proved that these operators that I just described generate a huge algebra which is known and has many interesting properties. So this algebra is kind of one of the central objects in the topic. So what are the operators again? So we have operators with just tangent multiplication by, let's say, exterior powers of the topological sheaf. They don't change the degree, the number of points. So that's why the first index is 0. And there are operators P1, K, which increase the number of points by 1. And also there is the twist by k's power of a line bundle. And then we can combine them. So for example, if we want to add 2 points, we can add 1 point and twist line bundle, and then we can add 1 more point with by another power of line bundle, and do various combinations of these line bundles, and in principle we get many interesting operators. And the question was, before this was, how to control all these things. So you can get tons of different things and tons of different operators, but somehow what is very good about this theorem is that you have some control and you can identify the algebra generated by these operators. So I wrote here a half of algebra because you can also consider lowering operators where you lower the number of points by 1. This would be the full algebra A that is here. So this algebra has many names. It is known, at least, to be isomorphic to so-called elliptic hole algebra, which was defined by Berman and Schiffman. It is also isomorphic to double affine cake algebra of L infinity. So it's some appropriate limit of double affine cake algebras of GLN. And then it's known to be shuffle algebra or Dean-Gilhar algebra. And that was the main result of Hagen's body. So there are many interesting definitions of this algebra, and all of them give different sets of generators and relations. And so, in principle, this is a very handy tool to deal with. And of course, because we deal with equivariant K theory, all these relations will depend on two parameters Q and T, which correspond to equivariant parameters on C star squared. So one particular feature of this algebra, which is surprising but which is known in any of these definitions, at least in first two, is that there is a huge group of automorphisms. So there is an action of SL2Z on this algebra by automorphism. And probably I should have done this with the picture. So one way to visualize this is actually to say that there is the lattice. Let's say this is the origin, and there are two coordinates, and for each lattice point you have actually an operator, which I will denote by P and comma. And then the operators which we constructed before are sitting on this line, where I have here like P 0, n, and they don't add anything, so there is P 0, 1, P 0, 2, and so on. And there are some operators on this line which are called P1, n, which increase the number of points by 1. But in principle, there are plenty of other operators which I would call Pm, n, which increase the number of points by m. And I will give some geometric description of that. But at least in one definition of this algebra, this elliptic hole setting, you can define it as an algebra generated by the symbols Pmn, and then there are some relations which you can read off from this lattice. So like commutators of two things is some other combination of PMNs which is very explicit. And in this setup, the action of SL2Z that you have is just the action of SL2Z on this lattice. And all relations can be read off from the lattice and they're invariant under this SL2Z.
So n is allowed to be negative?
N is allowed to be negative again. So I don't want to say too much about this, but again, there are lowering operators where you have the same correspondence, but you go from Hilbert scheme of n plus 1 points to n points.
Right, but I mean n, not n.
Yes, it can be negative.
Yeah.
And that is fine, like you can squeeze by negative power of line bundle. So that is not a problem. And again, more formally, you can say that if you have an action of SL2G, then you can just start from some point, some line, like vertical line, probably here it is horizontal, but anyway, and then you rotate it by SL2C, you get some new operator from this algebra, and we can call it PMN. But it is just the notation recording this is obviously Eugene. So this is a huge structure, and the question is how can we describe this PMN geometrically? So we describe some of them geometrically right now, but for all of them, we need some extra construction, and that will be the main subject of the talk. So we'll need the moduli space of the nested Hilbert scheme, which is the moduli space of long flags. Before we use the flags of length 2, where I have ideal and inside another ideal, here we have the moduli space of flags from codimension k ideal to codimension k plus n ideal. And there is a chain of these ideals, and I want the first of them to have codimension k, the next codimension k plus 1, and so on. So all quotients will be one-dimensional. And I want all quotients to be supported at the same point, let's say the origin. So that's my choice, but it will be a very useful choice. And of course there are two projections. So one is to, there are actually n projections. You can project to any Hilbert scheme that you have here, and this corresponding will be something. But in particular there is a projection onto the first ideal and to the last ideal, and we can use them to define some correspondence. And there are n different line bundles on this thing, where you can take jk over jk plus 1, jk plus 1 over jk plus 2, and so on. So I will call this bundle Li. So how this is all related to the Hilbert scheme that we had before. So if we have Hilbert scheme, this nested Hilbert scheme of 0, 1, and 2 codimensions, then this is exactly the same as usual Hilbert scheme supported at the origin, because somehow you can choose the maximal ideal uniquely because everything is the point. So this is exactly the same P1 that we had before. So if we have 3 points, then it is bigger than this cone over singular cubic, which was the Hilbert scheme of 3 points supported at the origin. So it is actually blow up of that thing at a singular point, which is isomorphic to the Hilbert surface of the third one, P1. And this is smooth. So this is a smooth P1 bundle over P1. And there are clearly 2 natural line bundles on it, and these line bundles are precisely L1 or L2 in this picture. And in general, unfortunately, it will still be singular, and it will still be not so good, but some properties, at least like we see in this example, are slightly better than for the partial Hilbert scheme. Okay, so that's what I just said, that the fly Hilbert scheme is singular, and actually it is reducible, so there are many components, and it's not so easy to describe all these components that we have here. But there is a way to define a virtual tangent bundle to it, and actually there are 2 equivalent ways to do this. And you can prove, and basically my collaborator Andrei Negut proved it, that it's a virtual local complete intersection, and it is expected, and at least we definitely expect that it is an actual complete intersection, but it is a work in progress. So you can think of it in many different ways, and one way is, if we go back to this picture, that you can realize this Kirstenbrook surface, this P1 bundle over P1. So what is this P1? This P1 is this, the Hilbert scheme of, the flat Hilbert scheme of 2 points. And then if the choice of third point will give me a P1 bundle over that. And in general, you can build it as a projective tower, where the fibers are projectivizations of some sheaves. So in principle, it's not so good because the sheaves the rank of the sheaf can jump or not jump, but at least you can use it to define this virtual structure and virtual tangent bundle. So the big theorem of Negut said that we can describe these operators P and M in terms of these long correspondences on the Hilbert scheme of points. So suppose for simplicity that n and m are co-prime, and then the operator Pmn is defined as follows. So again, we start from some sheaf on the Hilbert scheme of R points. We pull it back to the correspondence, and we twist with this strange line bundle on the correspondence. So it's a product of elementary line bundles and some strange powers. And then we push it down to a Hilbert scheme of R plus n points. So what is the strange line bundle here? So we need to use the parameters m and n somehow. And the parameters m and n are used in this strange way that I make this combination like integer part of mi over n, mi minus 1 over n. And there is some reason, of course, for this. And if you use these particular powers for line bundles, then you get the operator, which is exactly the same Pmn that you can define using SL2D action on the column. And in particular, if you take this Pmn with these strange powers, you will get that mutation relation that you would expect from topological fiction. Anyway. And again, in principle, if you just want to build some interesting sheaves, then you can take any powers and it would give you some. Okay? So now, this was about geometry and a bit about algebra and combinatorics, so how to write it down and how to use it for some computations. We can try to localize all these correspondences at fixed points and see how they add. So we said that you have an action of C star square on the Hilbert scheme on points and on symmetric power. Actually, you can leave this action to the flat Hilbert scheme as well. You can scale these ideals without any problem. And then a fixed point on this long correspondence is actually a tuple of Young diagrams. We have Young diagram with k boxes, Young diagram with k plus 1 boxes, Young diagram with k plus 2 boxes, and up to Young diagram with k plus n boxes. And all of them are nested, so one sits inside another. And there's a in one-to-one correspondence with what is called standard Young tableaus of skew shape, where I have two different Young diagrams, which is the first one and the last one, and then I write the numbers in a way how I add boxes one by one. So, for example, in this picture, I have an empty Young diagram with two boxes. Then I add this box and I get a three-box diagram. Then I add this box. Then I add this box, this box, and this box. So this will give me a particular chain of monomial ideals in the flat Hilbert scheme, and this will be a fixed point of torus action on this 2, 3, 4, 5, 6, 7 nested Hilbert scheme. So all fixed points are just like this. You start from some Young diagram, then you add boxes one by one, and then you end up with your final diagram. And then you can use localization theorem of a T-bottom left. So again, in case of flat Hilbert scheme, you have to be very careful because it's singular, and you have to use some kind of virtual localization and then measure it with actual things. But at least on combinatorial level, you can say that the K theory is isomorphic to the sum of K theories of fixed points. So this is can be identified with the space of degree n symmetric polynomials in infinite number of variables. So the direct sum of all these K-n's can be identified with the space of all symmetric polynomials, and this is just degree n p's. And the fixed point basis, so the fixed points are labeled by Young diagrams, and they can be identified as so-called modified Macdonald polynomials in this thing. K sub n is equivariant K theory of Hilbert scheme of n points. So again, you have fixed points which are labeled by Young diagrams. So the rank of this is the number of Young diagrams with n boxes. So this is the same as dimension of the space of symmetric polynomials. And again, the fixed points can be identified as Haiman's modified Macdonald polynomials, which I don't want to do for sure. But there is some explicit way to say which symmetric polynomials correspond to fixed point. And you can, so some of these operators which I didn't describe but which correspond to this horizontal line, they will correspond to multiplication operators by power sums. And then these operators on the vertical line, which we described, they can be identified as McDonald operators. So their eigenvectors are fixed points. So they diagonalize in McDonald basis. And then localization to fixed points provides a formula for matrix elements of these operators of PMF. And you can write them as sums over these chains of Young diagrams or standard Young tableau, how they name.
Sorry, I understood the vertical operators, but the horizontal operators, do you have like a geometric description, or you just do that using the SLN?
You do that, for example, I mean, you can describe it explicitly, but you can describe them using this term. So, I guess if you do horizontal, then all these SIs will be zero, so you just pull back to this long correspondence and then you push forward.
Is there some algebraic stack hidden behind this lower integer part? Or?
Not to my knowledge. And
is there a reason for the lower integer, for the floor?
There is a reason, but it comes from relations between this PMN and the latest, but I mean, this floor kind of, you draw a line connecting the origin to this point PMN, and then you count integer points, and you see this integer parts. So that's one way to see this, but I don't know any of this text. Okay, so now, yes. So how does
another question?
Yeah. Sorry.
Just a previous slide.
Yeah.
This Pn0, you said that the P0n are diagonal in the basis. What about the Pn0?
They're non-diagonal. So P0n, they fix the number of points. So you just fix the number of points and you act on the given Hilbert scheme by some vector bundle. So they are diagonal in the fixed point basis. The other ones, they add some points. So they can be diagonal. So you go from one Hilbert scheme to another Hilbert scheme. The data cannot be diagonal, but let me give you an example in a second. So for example, P1, 0, how it looks like and what does it actually mean in terms of symmetric functions. So you can say that this is multiplication operator by P1, and there is so-called a Pierre Rule for Macdonald polynomials, where you take this Macdonald polynomial, which I didn't define, multiplied by P1 and expand again in Macdonald polynomials with one or box. And then the Pierre Rule said that mu here in this sum would run over all diagrams which are lambda plus one extra box. And there is some explicit combinatorial coefficient in front of it. So for example, this is one example of this Pierre Rule. You start with this Macdonald polynomial multiplied by P1. You get some polynomial of degree 3, and you expand it in the same basis. So, on general grounds, you would expect 3 different diagrams appearing here. But the Pierre Rule said that there are only 2. And these 2 are precisely the diagrams contained in the original diagram with 2 boxes. And there are some coefficients which are always cyclotomic, so they are products of some linear factors on the top and on the bottom. So geometrically, you can think of it as a correspondence between Hilbert scheme of 2 points and Hilbert scheme of 3 points. And actually this is just simple correspondence. And you can say that, so this ideal corresponding to this diagram contains this ideal, contains this ideal, contains this ideal. And this weight that you see here, it just comes from localization formula of this correspondence. So this is some ratio of tangent weights upstairs and downstairs.
What's QNT?
QNT are equivariant parameters. So this, all these polynomials, they depend on QNT, like everything depends.
So
and then,
are these literally the 2 actions of the 2 coordinates in the plane?
yes. So QNT are literally coordinates in the plane.
So different levels. Are they really different?
Well, you can't use the same length, right?
I've been been using T1 and T2.
Well, I know some people using Q1 and Q2 for that, but okay. So that's one example. So you can think of it just there is a classical Pierre Rule from back to Maudon and Stanley, which says how to multiply Maudon polynomials by P1 or by Pk. And you can actually think of it geometrically as just adding boxes to the diagram and then counting subtangent. Maybe a more interesting example that I like more for some reason is related to so-called QT Catalan numbers. So there is a particular line bundle, which is the top exterior power of the topological sheaf on the Hilbert scheme of points, endpoint. And you can restrict it on the Hilbert scheme of points supported at 0. And Haiman proved quite a long way that for this line bundle, all higher homology vanish, and the dimension of the space of sections is equal to this combinatorial number, which is known as Catalan number.
Sorry, why do you call it O1?
Because you can think of it as O1 when you blow up the symmetric power, then it is O1 of this blow up, somehow, which appears, but it's not, I mean, you can just call it O1. It's determined. But actually this is O1 which appears when you blow up the symmetric power and you get this.
When you blow up the symmetric power, what do you get?
You get Hilbert scheme. And on the Hilbert scheme you get this bundle. Okay. So you have this bundle. It's definitely equivariant with respect to scaling coordinates. And then if you compute the space of sections, you can compute just the dimension of the space of sections. So you can compute the equivariant character of C star square in the space of sections. And this is called QT Catalan number, and it has many interesting combinatorial properties which are definitely not for this talk, but I like them very much. So one particular result that we checked with Andrei is that this line bundle on the partial Hilbert scheme, on the Hilbert scheme supported 0, you can get by applying one particular operator of this family to 1, where 1 is a class of Hilbert scheme of 0 points on the plane. So you apply this operator Pn, n plus 1, and then you start from Hilbert scheme of 0 points, you add n points, you get some class on Hilbert scheme of n points, and the claim is that if you apply this operator, then this is possible. So this is, I guess, not so deep result, but at least this fits this Haiman's theory into more general theory of PMNs quite smooth. Okay, so these are two interesting applications of this thing. So now how this is all related to nodes. So let's switch completely from Hilbert scheme to these pictures, at least for the moment. So on this slide I have, I don't know how many torus nodes. So what is a torus node? You take a torus and you draw a line with some rational slope on this torus, and eventually it will come to itself, come back to itself. So this is, for example, the trefoil, which is the same as T32 torus node. So you go 3 times in one direction and 2 times in another direction. And for any pair of coprime numbers m and n, you can draw this picture and you will get some interesting ones. They can be quite complicated, like this one.
You can see one right outside this building in metal.
On the boundary of this, on the boundary of that metal thing, which I never remember. Okay, so what kind of non-invariants are we interested in? So I definitely realized that almost no one here knows anything about non-invariants, so I won't define them for that purpose. But I will be interested in some particular invariants which are called Calover-Sturchy-Tiki derived invariants. And at least, what are they as an object? So we need to specify number n and a Young diagram lambda, and a knot, which, let's say, one of these knots on the previous slide, which is a torus knot, And as an output, we get a polynomial in one variable q, which is called colored Rashidin invariant p lambda n of q. And for different n's and different lambdas, you can get, for example, Jones polynomial, which is mono, better known, or colored Jones polynomial, or as a ln, skein invariance, or some other things. And you can actually eliminate this parameter m capital by introducing some variable a, and one can check that there is a polynomial in two variables, and when you specialize a to q to the n, you get back all this regular Jones polynomials, or all this lambda n. So we're interested in, so there is a way which knot theorem gives you, which to every knot assigns a polynomial in two variables a and q. And Khovanov and Rozansky recently developed a knot homology theory, which assigns so-called Khovanov-Rozansky homology to every knot. So this is collection of some homology groups. And the only characteristic of this homology is this bivariate Holmes-like polynomial. Actually, for lambda is equal to 1 box, but that's true. And it's known that Khovanov-Rozansky homology has some deep and non-trivial geometric meaning, but nobody knows what this is and how. So, for example, you can use Khovanov homology, Khovanov-Rozansky homology for bounds of genus of a surface with boundary of this curve and many other things. But the most unfortunate thing about Khovanov-Rozansky homology is that it's very hard to compute. So the definition is combinatorial. You use knot diagram and you build some complicated algebraic construction. But explicit computations are very hard. So if you start from some, like, I don't know, 7-4 torus knot, you'll have many crossings here, like 1, like this. I don't know. Some large number of crossings, and for each crossing you do some complicated algebraic construction, like find some bimodule, tensor, then compute for homology, and this is very hard. And in a recent work, Aganagic and Shakirov defined completely different invariant, which is called refined Chern-Simons invariant for torus knots. So unfortunately, it's defined rigorously and mathematically only for torus knots, but the definition is very nice and explicit using McDonald polynomials. And their motivation came from string theory and M theory, which I guess I will never understand. But in all examples, these invariants that they define actually agree with Poincare polynomials of Khovanov-Rozansky homology. So if this construction agrees with Khovanov-Rozansky homology, this is a very explicit and very effective way of computing this homology. At least for torus knots. Potentially it can be extended to other knots. So here is our main result with Andrei, that there is an explicit formula for this refined Chern-Simons invariant of Aganagic and Shakirov, and it is given by this formula, which is a huge sum over all standard Young tableaus of size n. And here is a product of numerous factors. So let me just not try to read the whole formula, but to describe some ingredients. So these chi i's are the contents of the boxes in T. So if you have a standard Young tableau, as we said, so we start from some diagram, and in this case we start from empty diagram, we add one box, then we add one more box, and then we add one more box. And then for each box you can define what is called QT content. So in this case it will be 1, this will be, let's see, Q, this will be T. So this is an equivariant weight of the monomial which sits in this box. And these are chi i's in this formula. Now these S i's are these strange powers that we already saw. So these are strange combinations of integer parts. And indeed they are exactly the same. And this omega is a function which appears all the time in the theory of McDonald polynomials. And actually it has some geometric meaning. This is the product of 1 minus x, 1 minus qtx, 1 minus qx, 1 minus. And then you have this huge product, and then you basically sum all these huge products over all 10 tableaus, and you get this invariant. So there are some versions where you can do slightly more, but this is what happens for one box, and actually we can do it for any number of boxes, but the formula will be just worse. Okay, so how this can be proven, and how this is related to all geometry that we've been discussing before. So, what is the idea of proof first? So, and what is the idea of construction of this thing? So, what does the physics say about this non-invariance? So, you run some topological quantum field theory, and to a two-dimensional torus, they assign some vector space with distinguished vacuum vector, which I will denote by 1. And then, if I have a solid torus, then for every node in the solid torus, there will be some vector in this space associated with this two-dimensional torus. And then there is an action of SL2Z on the algebra I. And so you have a vector in this boundary, and you have an operator acting on the boundary. So again, you haven't seen this, so let's just see this. I don't want to give too many details here. And there is an operator acting on the space Z of T2, and there is an action of SL2Z on this thing. And again, this action was defined using the work of Khovanov-Rozansky and Shakirov in the beginning of 90s, where they studied Aganagic and Conjecturally.
Is the algebra covered by the WNN thing?
Yes, I'll get this to the next slide. So, I mean, that's one of the checks that we need to make sure. The WMN will be exactly the same as PMN. And then, if you want to get a non-invariant in a sphere, you glue it from two solid tori. So you have two solid tori with a common boundary, which is two-dimensional torus. And one of them will give you this vector WMN applied to 1, and another will give you some topological vector, which, let's say, V of A. And finally, the non-invariant is a pairing of this vector coming from one solid torus and this vector coming from another solid torus. And
U of A is just S applied to vacuum.
is S applied to vacuum, right? But you need to be careful because S is not defined in the beginning. But yes, it just S applies to vacuum. And now, how this is related to all what we've been discussing. So the space assigned to two-dimensional torus is essentially the escape theory of all Hilbert schemes altogether. So this is a bit of a lie because it's a quotient of this, but let's say just the whole thing. So the whole equivariant case theory. And now, using some deep results of Cherny, Schiff, and Vassarov, we can actually prove that this WMN, which were defined using Magdalene polynomials and just explicit formulas, they actually can be made with PMN and the operators which appear in the story. And then this vacuum vector represents the class of a Hilbert scheme of 0 points, as I said. And this S applied to vacuum, and whatever, so this thing coming from the second solid torus, can be identified with explicit sheaf on the Hilbert scheme, which is just a generated series for exterior powers of the dual topological bond. And this is actually probably okay. So the non-invariant equals to the pairing of this PMN or WMN applied to 1 with this vector. So geometrically, we just compute the following equivariant integral or equivariant characteristic of the following thing. So we take PMN applied to 1, we get some interesting shift on the Hilbert scheme of n point. And then we tensor it with exterior power of topological, and we take equivariant characteristic of this whole thing. And the theorem that we had before is just a localization of that formula. So you can see some ingredients here, and these SI are the ones which come from the line bundles on the correspondence defined in PMN, And these all factors actually are just some tangent weights on the Clark-Hilbert scheme and virtual tangent weights on the Clark-Hilbert scheme. And all of them can be computed explicitly. So, yes. So, I have two last remarks. Actually, I'm almost done. So, one remark is that, for example, one interesting case would be when n is equal to 3. So, when you have Hilbert scheme of 3 boxes. So, if you write this formula, you'll have tons of different factors. And the number of factors, I don't remember, but it's really huge. But if you write it carefully, then everything will cancel out. Because the Clark-Hilbert scheme of 3 points is smooth. Because it just that Hirzebruch surface, which is the blow-up of functional Hilbert scheme of 3 points. So on that Hirzebruch surface, you define some explicit line bundle, maybe twisted with some this A generating function for exterior powers, and you compute the equivariant Euler characteristic of this line bundle, and this gives you a non-invariant for 3-strand torus knot, for example. So this is very explicit, and you can check. And this actually is known to agree with Khovanov-Rozansky. So this is not something superficial and this formula looks scary, especially when you see it for the first time. But if you localize on the Hirzebruch surface, essentially you will have just 4 fixed points, and then on each fixed point you know what to do. So 4 fixed points in this case are just 1, 2, 3. 1, 2, 3. 1, 2, 3, and another thing. So there are 4 fixed points on that Hirzebruch surface. In each of them, you have to compute the fiber of that line bundle and the tangent weights. But again, it's all quite straightforward. And then you compute it, you get precisely this formula here, after all cancellations. And generally, you will have just more factors, and there are some cancellations, and you have to be careful because it's singular, but again, this kind of virtual LCR argument says that everything would cancel. It should. So you will get some explicit formula, and this indeed agrees with Aganagic-Shakirov invariant and Hilbert, and conjecturally, this would agree with Khovanov-Rozansky homology. So what does it mean it agrees with Khovanov-Rozansky homology? It means that we have this sheaf here, and we said that we integrate or we take the equivariant Euler characteristic, but actually we can take homology. So the next conjecture here that the homology of the sheaf will be precisely Khovanov homology of the corresponding torus knot. And again, for small examples, it's proven because Khovanov homology, Khovanov-Rozansky homology are known. In general, it's widely expected.
So when you say for small examples, how small?
Like all 3-strand torus knots. So again, that's maximum that Khovanov and Rozansky can compute. So there are some higher examples, and there are some structural properties that you would expect that definitely hold here. But again,
your version would be easier.
yeah, it's definitely easier to compute than Aganagic and Shakirov, because in their construction you need to use some matrices of variable size, and you multiply them, you compute some traces. So this is explicit formula. You can plug in the computer and check it. So this is definitely a simplification of Aganagic-Shakirov formula, but again, and at least it's some geometric candidate what this homology may look like operating. So that's one remark. And another remark is that some of you may have heard of another interesting subject relating Hilbert scheme of points on a singular curve and not invariant due to Oblomkov and Schende. And this is completely different from this. But the expectation is that their invariants are the same as this invariant. And in some cases we know that this is true. In some cases this boils down to some combinatorial equation. And again, if we discuss the physical things, so the two should be related by some version of anterior thing. So they're completely different. I just want to say that they shouldn't be confused. And I think I stop here. Thank you.
Thank you very much.
can't probably define all these constructions. It's not known what is the algebra that we get from this correspondence. And it's not known how to relate to not theory, to my knowledge.
I mean, is there a reason why things are connected, like the whole theory that it was, or is just something that compatible?
And essentially, the question that this algebra is intrinsic. I mean, it is kind of the most natural algebra correspondences on the Hilbert scheme. This appears in non-series. So that's the relation from me. But again, the deep Aganagic relation would be against and theory without. No. I mean, you don't see it on C2. No, the latest somehow acts by some non-trivial automorphism with the solver. And there is some relation of this with torus. So. That's nonsense.